In this video, we are going to explore 6502-6510 assembly language programming on a Commodore 64, just like it was 1986. We're going to see how to type in an assembler from a magazine and use it to build some simple programs. We'll analyze those programs in a machine language monitor and explore how the computer runs it. We're going to do this on a plain Commodore 64 with just a single 1541 disk drive. I don't actually have a real Commodore 64, so I'll be doing this video through the wonderful Vice emulator. The assembler we're going to use is called Fast Assembler, and it was published as a type-in program way back in January 1986 in a magazine called Compute Gazette. This assembler was the cost of the magazine, which was about $3 to $4, so a really good deal actually. This is an interesting assembler because it's not a standalone program that you run to assemble source files, but instead it's almost like a whole new version of BASIC that supports assembly language. It's really, really fascinating. You assemble your code by wrapping and running in a BASIC program, and the assembler itself is tiny. It's only 2600 bytes of memory. The machine language monitor we'll be using in this video is called 64mon. I chose this monitor because it's referenced a couple of times in a programmer's reference guide, and I always wondered what it was like to use it, so I picked up and started playing around with it. 64mon can be found on the Commodore Macro Assemble development system, and it is a file called monitor $8000, which means we can load it and type sys32768 to run it. But more on that much later. You should be able to find these two programs as D64 disk images on the internet in case you want to grab them and follow along, but don't really want to type these in, and I totally understand it. So, with that said, how do we type this assembler in? So here we are on page 132 of the magazine, and you could see the raw machine language in hexadecimal format and just columns of data to type in. So you're thinking to yourself probably, well, how do I key this in? Well, luckily it says see the instructions in the article on page 78 before typing it in. So let's go take a look at that. So here we are on page 78, and there's a little section here called typing instructions. It says you'll need a copy of the new MLX program appearing this month for the first time to type in Fast Assembler. Oh, okay, so we need to key in another program. Okay, so let's go find that. So here's the article about the new MLX, a new program to make typing in machine language programs for the magazine much quicker. So this looks pretty interesting. So we'll go down to the actual program listing. And you'll notice next to each line there's a rem statement with a 3-digit number. That's actually a checksum, and that helps you type in this program accurately. But you need a program that calculates a checksum while you type it in. That's in another part of the magazine, and that program is called the automatic proofreader. So finally we arrive at this page, and we got to type in the automatic proofreader. Luckily, this program is really short and includes a little tiny checksum of itself to make sure you keyed it in correctly. This program only took me about 10 minutes to type in. With that typed in, we're ready to start typing in MLX. So with this program typed in, you'll notice that anytime I press the enter key, the little checksum appears at the top left corner of the screen. Cool, so now we'll go back to the page with the new MLX listing, and we'll start keying that in. This is kind of what it's like to key it in. And you'll see the top left corner, a little 34 appears, and that matches what's in the rem statement here. So I typed this in. It was about 15 minutes, 20 minutes to type in. And then, of course, there were a few lines I got stuck on where I had to type it in just seemingly over and over again because I kept making small typos that I just couldn't pick up. Thankfully, the automatic proofreader let me key the program in, and now I was ready for the main course, to key in the Fast Assembler. So the key in the Fast Assembler, we have to load up our new MLX program that we just typed. So in the instructions, they tell you to put the starting address of 0801 and the ending address of 1220. Then it's going to ask you if you want to clear the workspace. What this does is it fills that entire memory address range with zeros. So we're going to click yes. So the reason why you click yes is so you can see how far you've gotten. We haven't done anything yet. So if I press D to display data and you type in the memory address, we'll type in 0801, you'll just see zeros. So now let's enter some line of code starting at 0801. As you can see, this is going to be about as exciting as watching grass grow. But here's how fast you can key a line in generally. If you get it right, you get a bing and you get a chance to move on to the next line. If you get it wrong, you get a buzz. Now you can visually spot check it. In this case, I typed the D6 by accident. It should be a 7. And then I can continue on. It took me, I don't know, 3 or 4 sessions of about a half an hour each to key this in. Definitely not the most exciting time of my life. But once it was completed, I now have the satisfaction of having a new assembler to play with. So now let's check it out. As you can see, Fast Assembler presents itself as a new version of BASIC, and it really is an enhanced version of BASIC. It's going to give us a whole bunch of quality of life commands and enhancements to the basic system that's in the computer, as well as, of course, the ability to assemble code. The way it assembles code is really interesting. It assembles code by you running your program, and while it's running, it'll look for machine language statements and assemble those. And then basic statements, it will run as regular BASIC. So to see this in action, let's put together a super simple assembly language program that's going to simply set the border to blue. I'm creating a separator line just so we can visually separate the basic code from our assembler code. Once we start mixing it together, it can get a little ugly. So we want to do our best to keep our code clean and readable. Yeah, I was pretty good at track and field back in the day. Not the real track and field, of course, on a computer. So we can create a label called start. That's going to represent the start of our code. I'm going to load the accumulator with a value of 6. That, of course, is blue. We're going to store that value into memory just D020, which will change our border to blue. And then we have an RTS, which is a return from subroutine, which is going to bring us back to basic once we launch this program, and then it's finished. So now we need to tell the assembler where in memory we want to assemble our code, and we do that with the org command. The origin command, or the org command, instructs the assembler to assemble our code into C000. Now this is a 3-pass assembler, so we have to run our program 3 times in order for it to fully assemble the code before we can put it into object code. And we do that with a for next loop. At this point, we have 3 lines of basic. That org command is an extension to basic. And then we have our block of assembler code in the middle. It'll run through the 3 passes. It still hasn't put our assembled code into the C00 location yet. We have one more command we have to do for that, and that command can only be run on a 3rd pass. So that is another call to the org command, but we're adding a (1) to the end of it. The second parameter org is called the mode. Mode 0, which is the default value, which is why we didn't have to put it in line 50, is just a regular pass through the code, building the tables and whatnot, whatever it does during assembly. On the 3rd pass, we're going to tell it, hey, all that code you assembled, now write it into $C000. So if I run this program, it looks like nothing's happened, but it has indeed assembled this to memory. So before we run it, we're going to save it to disk. Always save your programs before you run machine language. When machine language goes south, it usually takes the whole machine with it. All right, let's give this a run. And our border turned blue. Now for all you basic programs out there, you probably just noticed, hey, did you just pass $C000 to a sys command? Yep. One of the cool extensions that Fast Assembler gives us is the ability to use hex in BASIC. We can also use binary in BASIC. So if you start a value with a %sign, it's rating as a binary number. That gives us 2. That gives us 6. And of course, 255. Pretty wild. You can also do 16-bit versions of it. 65535. So let's add a little bit more feedback to this process. So because we have control of BASIC, we can actually add in some other things when we run the program to provide feedback during the assembly process. So for example, maybe we want to print out which pass that we're processing. So we could, at line 70, print the pass. So we can see the 3 passes as it runs through them. We can also use the labels as variables. So at the end of the assembly, we can print out the start address. So we kind of know the start address anyway from the org command, but what about the end address? There's a variable called asterisk, which is the program counter, and at any time you print it in the assembly process, it'll tell you what memory address it's looking at while it's assembling the code. So at the very end, it'll tell us where our program ended. So we can add something like this. And now we can see the beginning and ending address of our program. We can also do expressions with it. So here we can see the start and end address of our program and how many bytes it is. In this case, it's 6 bytes. If you inserted that start in the middle of the code, so for example, at 1025, I mixed it into our assembler code, you can see the value of where in memory that particular line is while it's going through the assembly process. Now, of course, it looks pretty ugly, so let's get rid of that 1025, and let's reformat 70. So you can see I'm doing my best to keep everything kind of formatted so it's easy to read. A quick note about assembly language. Again, that's the lines 1010 to 1030. Assembly language is generally structured into 4 columns. The first column being where your labels and equates are, and again, we'll get more into that in a little bit. The second column is where your mnemonics go, LDA, STA, etc. The third column is where the operands go. That's the parameters for the mnemonics. And then a fourth column, optionally, you can put comments. Now, this particular assembler doesn't really care about formatting. In fact, I could write the code like this. I could write it all in one line of code. It's not very readable. It's not what people are expecting to see when they write assembler, but you can do that and nothing would stop you. And maybe there's a case where that actually would be more useful, more easy to read. So we can get rid of that. So let's resave this. So now let's explore how the processor runs this code and also how to use a monitor to debug it. So we're going to load a monitor in. This monitor is called 64Mon, and I was able to find it on the Commodore Macro Assembler Developer System. It's referenced a couple times in the Programmer's Reference Guide, although they reference it on cartridge. I haven't looked very hard, but I haven't seen a cartridge image for it, but we're going to be running it in software form. The 8000, if you're not sure what that is, we can print it here, 32768, and we can run it that way. Or we can run it with our $8000. And now we're in the monitor. Any software monitor you have is going to look pretty similar to what you see here. We're going to cover each part of this in detail as we kind of explore how the computer runs this code. So for now, we're going to ignore what you see there for a moment, and we're going to use a disassemble command. We know our program is 6 bytes long, and it was assembled into C00, so let's take a look at it. So the D command stands for disassemble, and you put a starting address and an ending address. And there's our code. So let's talk about what we're looking at here. The first column with the memory addresses is the memory address where that first byte to the right of it is. So for example, the first byte to the right of C00 is A9. That middle column that contains 3 columns of bytes is where the opcode is and the operands for it. And we'll get into that in just a second. And then to the right of that is a disassembly of the source code. Now, this source code looks exactly like what we just wrote, but when you start using labels, you'll see that the exact memory value here, but in our source code, it's going to be like a variable. So now let's talk about what happens when you run a program. In this little graphic here, you can see that the memory address of our code is C00, which is kind of a little off to the right of center of memory. And you can see a call out that I made, which is the view from the monitor. So what happens on your computer is there's the microprocessor, in this case the 6510, which is a 6502 variation, has a 16-bit register called the program counter, that's PC. And when you type in sys $C00, the program counter is pointing at that first instruction. And that first instruction is A9. Now if we go into the Commodore 64 program as reference and look up that mnemonic, LDA, you'll see there's a little chart for each mnemonic. LDA is load accumulator with memory. So the accumulator is a spot on the CPU that stores a value, an 8-bit value, and it's actually on the chip. So what this is going to do is take the value next to it, the 06, and copy it into the CPU chip. And that is called immediate mode addressing. And in this chart, you'll notice that A9 is the immediate mode opcode for LDA, for load accumulator with memory. So once we do that, the computer moves over to the next instruction, which is at C002. Now it has an opcode of 8D. So again, if we go to our Commodore 64 reference guide, we can see that 8D is the addressing mode called absolute. It's that third entry in that table. So what absolute addressing mode does is the CPU takes the next 2 bytes, which is going to be a 16-bit memory location, and it's going to store the accumulator into that value. Now, what's interesting about it is the disassembled code on the right says D020, which is what we typed into our assembler code, but in memory, you see it backwards, 20 and D0. That's because the CPU is expecting memory addresses in what's called little endian notation, where the smaller value appears before the larger value. So when you see the real bytes that the CPU is going to process, that's how it's presented. But as human beings reading assembler code, we look at it as big endian order where the bigger numbers are on the left. And then of course, the last command is RTS. So the last question you might be thinking to yourself is, how does putting a value into memory change the border color? Well, the CPU is not the only thing on a motherboard looking at memory. There's another chip on a motherboard called the VIC chip, the video interface chip, and it is constantly scanning memory for information on how to paint the screen. So while it's constantly painting the screen over and over and over again, usually about 60 times a second, at least in North America, every time it draws the border, it's always looking at that D020. And once it sees our new value in there, it immediately changes to that new value. Even mid-screen, it'll change that value. And there's other chips also constantly looking at memory, things like for sound, things that write to memory, like the joystick ports, like what direction the joystick is being pressed, all sorts of stuff. So the vast majority of programming the Commodore is looking at memory maps to see what interesting places you can poke and prod values to control or to read from peripherals on the computer. So now looking back at the block of text when we first started up the monitor, we now know what 2 things are. We know that PC is the memory address where the computer was running code from. So when we entered the monitor, the PC was running code at 803E, and at the accumulator it was 0. We'll cover the other registers when we get to them. But at this point, we're done with the monitor, and we can exit out of this by using the X command. Now that we're out of the monitor, you would think you could type list and continue on. Not quite. The monitor does corrupt some of the areas of memory that the assembler was in when we run it. So we have to restart the assembler. Luckily, it's pretty easy. We just type in SYS 4408. All right. Now, if I type in list, my code is still gone. The machine language monitor gives you a command to look for it and bring it back. And that command is old. And our code is back, and we can now rerun it and continue on with adding code. And then if we need to, we can bring the monitor back in to debug it. So one of the really nice things about Fast Assembler is I have my assembler memory, I have my monitor memory. So I'm very able to easily write code, assemble it, test it, and debug it without having to restart the computer to load other software over and over again. So it's a pretty nice program. And we use this as a template to build new programs to explore more features. So let's restart and try a new project. We're going to now explore subroutines and how to call them and how to move them to a separate file. We're going to start by loading our template project in. We're going to quickly change the name of it from test to, I don't know, sub for subroutine. Okay. And then we're going to make some really simple changes to it. We're going to add 2 lines of code before start. So this will become the new start of our code. This will become our subroutine. So from here, we're going to call JSR set B. And then here, we're going to return from subroutine. So our program now will start. It'll call a subroutine to set the border. The border will do the work. It'll return from the subroutine back to the basic line 1009. Then the program will end. So let's save this up. Let's run it. Okay, we're going to load in our monitor. Before we run the monitor, let's just take a note here that our program output is 10 bytes. That's going to be important to know. So now we're in the monitor. Now, of course, this monitor message is a little bit less cryptic than it was before. PC we now know is a program counter, where the PC was before it got into the monitor. We know that the accumulator is an 8-bit value that we can use. A new register, and that's the stack pointer, an SP. So let's first decompile our code and take a look at what it looks like behind the scenes. Okay, this is our assembled code of what we just wrote, minus the very last line of the BRK. Now we could see it's a little different than our source code was. In our source code, we wrote JSR set B. The assembler resolved that to an address C004, and that's what we're seeing in this output. So now let's explain what the CPU does when a JSR is encountered. So let's take a look at this quick graphic. We can see there's a block of memory that is sectioned off just for the CPU, sort of, for the stack. And it's called page 1. Page, when you take a 16-bit address, there's 2 8-bit values to it. There's the left value and there's the right value. The left value is the page number. So when you see addresses that start with $01, that's page 1. And that is the area of memory that the CPU uses for the stack. Well, now, with that said, what is a stack? If you imagine the stack is this kind of bucket, if you will, and you'll see that there's numbers on the left side of it, F6, F5, F4, F3. Those are the locations of what's called the stack pointer. The stack pointer in our CPU starts at F6. And when you put a thing into the stack, it'll write it at F6, and then the stack pointer will go to F5. So the stack pointer represents the next free available space of memory. The stack pointer moves left or down in memory. So the stack is said to have start at the top of page 1 at 01FF and moves to the left. Now the CPU knows that the stack is always in page 1, thus it's able to use an 8-bit value just for the right value. So F6 in the stack pointer is really 01F6. So now what happens when I call JSR? The next instruction that's going to execute is at C003. So the CPU puts that address -1, so that'll be C002, into the stack. It puts the CO in first, and then it puts the O2 into the stack. So the stack pointer will move from F6 to F4. Now we can see that in action if we replace the RTS in C009 with a break. And you do that with the A command. So now if I disassemble this code, we'll see that we have a JSR to our subroutine, but instead of returning, it'll break. And we want to do that to inspect the CPU and its state at the time it gets that point of code. What break does is it returns control back to the monitor. So showing the registers here again, that's the R command. The stack pointer is 6. So if I tell the monitor to execute code at C00 with the G command, you'll notice that it set the color to blue, and now the registers are at the new state. So the register shows you that the stack pointer is F4, indeed, 2 memory addresses to the left of where it started. We can see our 6 sitting in the accumulator. So how do we prove that the stack has our memory address in it? Well, we can inspect the memory. So if we do an M, this is going to show us the contents of memory. Page 1, F4, right? Remember, F4 is the next free block of memory. Our address is sitting in F5 and F6. So here we go. F4 is garbage. It's just whatever happened to be there, 83. And then there's a return address in little endian order, O2CO. Now, if I were to reassemble C009 to be the RTS instruction, and then tell our monitor to continue from there, the RTS instruction, it's going to pull those 2 values off of the stack, add 1 to get C003, and then it'll put that into the program counter, and then the CPU will resume at C003, and then our program will end. So what we're going to do is make a small change again, and we're going to change our RTS at C03 to a break. This way we can see what happens when it comes back. So now we're going to run from C009. Once again, it breaks. And you'll see that the stack pointer has indeed gone back to F6. Our accumulator is still 6, because that's what we put in there when we were changing the screen to blue. And normally it would end the program here with RTS. And that's how subroutines work. So now we're going to exit out of our monitor. Okay, so we're going to restart the assembly with 4408, because as you recall, the monitor will corrupt the memory of our basic program. And then we're going to type in old, and now our code is back. So now we've seen this work, and now we have a good understanding of how we call subroutines from machine language. Now let's move the contents of our subroutine to a separate file so we can include it. So this would be kind of like a shared library. So this file is fine. What we're going to do is we're going to scrape off the assembler parts, because when you include another file, we're just including the assembler portion. We don't want to trigger another pass through the assembler. So we're going to get rid of 10 through 70, and we're going to get rid of 60,000 plus. So now we're left with just this. So now let's make our code a little bit clearer. We're going to get rid of this because we're not starting it. And maybe we'll put a little comment in here. We'll make this 1009. We'll make 1008 say something along the lines of sets the border to blue. And then we're going to change our file name to .i. That I will stand for include. I just kind of made it up now. It is whatever file name that you like to signify that. So now if I list it, that is going to be our included file to set the border. So we're going to save this as sub.i. Okay, let's reload sub. So now instead of having those 3 lines of code, we can replace it with include sub.i. And then we'll get rid of 1020 and 1030. So what this will do is that line 1010 will include the code for those 3 lines. Now, normally a subroutine would have a lot more code than that, and the benefit of that is much easier to read code. So instead of seeing all the logic for setting the background color, it's just an include. But there's a price for this. So let's first save this. And the price you pay is slower assembly time. So when I run this now, you'll notice that for each pass, it has to go to the disk to load that file in. So it takes a bit longer. So now you could imagine if you have like 13, 14 includes, it could add quite a bit of time to the assembly process. And running it, our border still turns blue. And that is how we do subroutines. So let's continue our conversation about subroutines by writing a subroutine to print text. So let's start by bringing our template project in. So what we want to do is we want to print text to the screen. So let's first define the block of text we want to print. And I'm going to put it at line 1400 right under our main code. We're going to use a new directive called byte, and that's going to let us inject bytes into memory right after our program ends. We're able to use screen control characters like we're using a print command. So there's a clear, white, the word hello world, and then at the end of it, we're going to put a comma 0. When we write the routine to go through this data byte by byte, that's going to be the way we know that we're at the end of our text. So now we need a routine that's going to print that text. So let's create a new routine starting at line 2000. So, let's also rename this. This is going to become, we'll call it PRT for print. So let's copy this in. And then we'll say print hello world text. We want to use a new type of register on our CPU called the X register, and they are considered index registers. The X register is just like the accumulator in that it's 8 bits wide. So what we're going to do is we're going to say LDX, which will load the X index register the value, and we'll set it to 0. This is going to represent the offset into the text block of bytes as we process each one individually. Here we're going to create a loop that's going to read through each character and print it. So what this command is going to do, it's going to load into the accumulator. It takes the value of the text memory address and adds X to it. We start with 0, so the first character to print is going to be clear screen. We want to know before we print this if we've read the 0 command in. So I'm going to use a new mnemonic called BEQ. But before we look at BEQ, we need to understand something about how LDA works. So looking at the cheat sheet here for the load accumulator with memory, you'll notice on the top right, there's 7 letters, some with checkboxes, some with underscores under it. These are called status flags. There's a 1 byte value on a CPU called the status register, and it holds an 8-bit value, of which 7 of them are used. 1 of them is not used. The one that we care about for this discussion is the one called Z, the 0 flag. And with load accumulated with memory, you can see here that this mnemonic can possibly set the N flag and the Z flag. Well, the Z flag is set if the value that was loaded into the accumulator is 0. That brings us to the next mnemonic, BEQ. It's branch on result 0. It will branch to a new location in our code if the Z flag is 1. So if a 0 was loaded to LDA, the Z flag will be set. BEQ will branch to p end if a 0 was loaded. Now if a 0 was not loaded, we want to continue forward. So there's a dedicated block of memory towards the end of the 64K that contains what's called the kernel. There are quite a few routines that come built in the Commodore that do things for us that we can call, and one of them is printing a character to the screen. As you can see here, CHR out is the name. It's at address FFD2. In our reference guide, there's a nice description of how it works. In short, the value that's sitting in the accumulator will be written to the screen. So once we've printed out that character, we're going to increase the value of X so we can look at the next piece of memory. And then we'll jump back to P loop where we can look at the next piece of memory, and a loop will continue until we see that 0. When we branch the P end label, we'll just have an RTS that brings us back to the caller. So how do we call this now? Well, up here, we're going to insert a line 1025. That's going to JSR PRT. And then down here, we just have to make sure PRT exists. So now our assembly looks something like this. We set our border to blue. We call it PRT label. The program counter goes to PRT. It does the routine to print the text screen, and it returns, and then our program ends. To make it a little bit more readable, we'll add another little line to the end here. Cool, let's save this and try it out. And voila, we've printed Hello World to the screen. So our PRT subroutine works just fine. The only minor problem with it is it only works with our label TXT. We want to be able to use this subroutine in other programs or even other parts of this program, so we want to change it in such a way that we can pass in the memory address of TXT as a parameter. So we have to make a couple adjustments. So normally, to call that, we would take the memory address of TXT and break it into 2 parts, because we have to pass it in the registers, which are only 8 bits wide. So to do that, you would normally do something like this. What this does in most assemblers is it puts the low byte of TXT into the accumulator and then the high byte into the X register. The problem is fast assembler does not support that notation. So we have to implement that logic ourselves. And we're going to do that by defining 2 functions in BASIC to do that. So the first function we'll create is one that calculates the high value. And this one's really easy. So we'll call it high, we'll pass in X, and it's going to be the integer of X divided by 256. The basic int function will divide by 256 and discard the remainder. The little slightly more complicated one is the low byte. So we'll create a function to do that, and it's going to be X minus 256 times the integer of X over 256. Okay. That takes the whole number and then subtracts the same math for the high part multiplied out by 256. We're going to insert an end here so we could test our 2 basic functions. Right? So we'll start with a number such as C001, right? So that's going to be 49,153 in decimal, and we know that the high value is CO and the low value is 01, right? So we could test our function out by asking what is the high value of C001, and we get 192, which is correct, right? Because if you wanted to know what CO is, it's 192. If we wanted to see the low value of that, we should get back a 1, which is perfect. So we know those functions are working correctly. So we'll get rid of our end here. And now over here, instead of passing in the less than, we have to call our function. Kind of a hack solution, but the code is still readable, so I'm not too upset about it. But it is kind of different than the typical syntax you would see in other assemblers. Okay, so now we have the accumulator and we have the X register holding the low and high parts of our text address. So how do we consume that now in our JSR function? Well, here's how we're going to do it. So we're going to add a couple lines above PRT because we have to do some work here. Okay. So indirect addressing means I pass you a memory address, it goes to the memory address, and then would add Y and then work from there. The problem is you can only do that with 0-page addresses. It's not a big deal. So we have to take the two parts that we have and store them in 0-page. 0-page is the first 256 bytes of memory. It runs from addresses 0000 to 00FF. Most of the opera have an address mode where if you pass in just a 2-digit memory address, the CPU knows that's for 0-page and looks at it like that. All right. So we're going to store this into 0-page because we're going to need that in a second. And 0-page, as you could tell by looking at this little chart here, is used by a ton of things in the operating system, in the kernel and BASIC and such. There's only about 4 bytes that are pretty safe for us to use, and they're between 00FB and 00FE. So we're going to store the accumulator into FB, and we're going to store X into FC. So now together, they're in FB and FC, and they form the little endian address of TXT. So we've passed it. We need to move our label up because PRT now starts here. Okay, now it gets a little tricky. You have to use the Y register to do this. So we're going to make this a Y. And then here, instead of looking at the pointer of text, we type it like this. Okay, this tells the computer, go to 0-page, look at address 00FB. Whatever memory address you find in FB and FC, that 16-bit value, add Y to it, and then that's the character we're going to pull into the accumulator. And now this function can be used by anything, as long as we split the address going into it, into the accumulator, into the X register. And I just noticed here that needs to be the X register. Okay, let's give this a shot. Well, let's save this first, and then give it a shot. So it didn't work, so we need to do a quick debug here. So I press run stop restore. It says 4408, type in old, and our code is back. And I can see here that I incremented X instead of Y. That's why the program got stuck in an endless loop. So we'll do this. We're going to save it again. Give this a run. And there we go. Now that we've finished our project, we want to be able to produce a program file that users can load and run on their own. It's a little tricky in fast assembler, so here's how it works. So in line 60, that's where pass3 happens, and we tell the assembler to assemble to memory. There's 2 more parameters we can add to that org command to have it also write to disk. And it works like this. We give it a drive, and we give it the file name. One interesting thing about that command is it doesn't close the file, so you have to close it at the end by yourself. So at the very, very bottom here, it's 6030, we have to close 8. It tells you in the article that file 8 is what it's used to write to the file. So we have to close 8 when we're done. So now if we run this, it should create the program for us on disk. Excellent, and then we'll just restart and try it out. And there we go. Very exciting. So my final thoughts on the fast assembler. On the pros, it is a tiny footprint. This thing is minuscule, 2,600 bytes. And they put itself like right before basic, so it really doesn't get in the way of anything you have in your machine. So it's very easy to get a machine language monitor, just about any particular one, at the same time as this assembler. So it really leads to a very fast code and debug cycle. You know, write some code, get into memory. If you need to look at it in the machine language monitor, you can jump into the monitor and look at it and then jump right back to your code. That cycle is really, really fast. And that's a huge pro to have. A lot of other assemblers have a much longer cycle to code, run, and debug. This one is just really, really fast. Having hex and binary support in BASIC was awesome. That is super, super useful. So this, even if I want to, figure out what number I need for bits, I can just print %, put the bit pattern I want in and see what the number is in decimal. So that was really nice. On the con side, though, man, managing the assembly process in BASIC is just not a great experience. When you're writing code, you're kind of writing two sets of code at the same time. Your actual assembly language code, and then kind of the framework to build it is mixed in with your code, and it's not fantastic. The other problem I had is if you had a typo in a label, so let's pretend you had a subroutine, you called it print, I don't know, PRINT, and you typed in JSR PRIMT by accident, instead of giving you an error that it couldn't resolve that label, it just resolves it to 0 and it just JSR 0. That was kind of annoying. I've run into that a few times because, sometimes I type faster than I think. And the other minor annoyance was not having load immediate calculating the low byte and high byte functions, the hashtag less, hashtag great. There's a workaround. We can declare the functions in BASIC, but it felt really hacky. And then when you look at the code, it's just not the typical symbols that you would see in most assembler language. But ultimately, that was a really fun experience. Man, that's a fantastic typing program. I kind of wish I knew of its existence, but I was a bit young when it came out. I think it was 11 when I got that issue of Compute Gazette, so I probably wasn't quite old enough to appreciate what a fantastic tool came in a magazine. That's really the ultimate pro right there. Is in 1986 in January, anyone that bought that magazine for $4 had a fully functioning assembler. I know there were type-in monitors. I don't know if it was in Compute Gazette, but I know other magazines, definitely books, had ones you could type in that were very useful. I think TinyMon, maybe Supermon. I think that was Jim Butterfield's. But in any case, for the time, this is a really, really cool tool. For writing assembler today, and if you want to kind of learn assembler, I think you'd be better served by using something like Merlin or Turbo Macro Pro. But again, man, what a fun time making this video. And thank you all for taking the time to watch and listen. Take care.